Okay, good afternoon, everyone. We are today going to finish up actually our new topics for energy, the energy unit, by talking about power. Okay, and power is one of those words that in everyday language it has a certain meaning, but in physics it has a different meaning, has a very specific meaning. So let's start off with an example. Let's say you have two people, they go to the gym, even though the gyms are closed right now. They are trying to bench press 60 kilograms. You've got Buff Bob, he is able to push the weight up 1 meter in 0.5 seconds. And we've got Scrawny Stanley, he struggles with the weight. He's able to push it up 1 meter in 3 seconds. So very clearly something different is going on here for those guys. Our first questions focus on how much work each of them did. How much work did Buff Bob do? How much work did Scrawny Stanley do? So if we're going to try and figure out how much work they did, what we're really talking about is how much work their muscles did as they push up on the weight. That happens to be the applied force. So ultimately what we're looking for here is the work done by the applied force, WA. And that's going to be equal to the applied force multiplied by the displacement multiplied by cosine of theta. Now, you can imagine someone trying to bench press. We all know what a bench press is. Hopefully, you're lying on your back. You have a weight over your chest on a long barbell, and you are trying to push that up. So the force in doing that is directed up. We know the weight moves up. Since the force and the displacement are in the same direction, that means that we are talking about two vectors that have 0 degrees, a 0 degree angle between them. Cosine of 0, as we know, is 1. So this is just going to cancel out and give us 1. We know the displacement is 1 meter. We don't yet know what the applied force is. In order to figure that out, we probably need a free body diagram. So let's draw that. What we're looking at, the object that's experiencing the force is the weights. Okay, we have an axis, x, y. Okay, and in this situation, we have an applied force pushing up on the weight. We have a force of gravity pulling back down on the weights. The net force in the y direction would then be Fa minus Fg equals May. I'm just going to separate that. Let's say, just to make this simple, that there is no acceleration. These weights move up at a constant velocity. If there is no acceleration, that term is 0, and we know that Fa is equal to, well, we know that Fg is really equal to mg. So the applied force is equal to m times g. We're going to bring that back over here. The work done by the applied force is equal to m times g times d. The mass of the weights that are trying to be bench pressed is 60 kilograms. G is 9.81 meters per second squared, and d is 1 meter. So we figure out how much work Buff Bob did. 60 kilograms times 9.81 times 1. And we end up with 588.6 joules. He gave that barbell, that weight, 588.6 joules. What he did was he increased the gravitational potential energy of it because he brought it up. Now, that's how much work Buff Bob did. Let's go to Scrawny Stanley. Scrawny Stanley, he's doing the same thing. He's lifting the same weight. So that, again, the equation is going to be Fa times d times cosine theta. Cosine theta is still going to be 1. The displacement's still going to be 1. Well, in order to figure out how much force Stanley needs to use, I guess we draw another free body diagram. Looks the same as before, okay? Same basic situation. And we see that the net force is, again, Fa minus Fg equals May. Again, let's assume no acceleration. Even though it took him longer, we can still assume a constant acceleration. I don't see a problem with doing that. So we're going to say that this is 0. And again, we're going to say Fa equals mg. And then we're going to plug that in over here, and we're getting the same equation, which isn't a bad thing necessarily, but wait a second. Scrawny Stanley's pushing up the same amount of mass, 60 kilograms. He's doing it with the same gravitational acceleration, 9.81 meters per second squared. Again, that's not the acceleration of the weights, that's just g, the acceleration due to gravity. It's a constant we need. And the distance is the same. It's the exact same numbers, so we see that Scrawny Stanley did the same amount of work. Huh. Now, if you and I were to watch this happening in a gym, we could tell the difference between these two people. Okay, we would say, well, Bob's better at doing this. It just looks better. Okay, but they do the exact same amount of work. So the amount of work that's done, the amount of energy that they have used is exactly the same. How are the two different? It lies in the times. Bob does his work in a smaller amount of time. Than Stanley. That's why we would assume, he is better at doing this. What we're noticing is not just how much work is done, but the rate at which it is done. And in physics, this is a certain word. We would say that Bob is more powerful. Or that he uses more power. Now, this leads us to the concept of power. Power is another defined quantity in physics that we can calculate. The definition of power is the rate at which work is done. The rate at which work is done. Whenever you see that word rate, that usually means that we're measuring something over time or with respect to time. Okay? And remember what work means. Work just means energy is transferred. So another way of explaining this is you could say that power is the rate at which energy is transferred. That's equally good. Okay, so the rate at which work is done. How much work is done over some time period? That pretty much tells you what the equation should be. Work done over time equals power. P equals W over T, and this is in your reference tables. However, there's a couple other equations for power in your reference tables, which I'm going to go over right now. We know from up here that work is equal to the force times the displacement, times the cosine theta part, but let's ignore that for now. Let's pretend that F and D are in the same direction. We could also figure out the power, instead of doing W over T, by using the force times the displacement. Again, because work equals force times displacement over T. And then there's even another equation, because look what we have right here. We have a displacement over time. What is that? That's from a long, long time ago. We know what displacement over time is. If you recall, from the very beginning of the year, displacement over time is the same thing as average velocity. Okay? Average, that little bar, over the V for velocity. So you have three different ways to calculate the power that something generates or something uses. The work done over the time, force times displacement over time, or the force times the average velocity. Not all those are always going to be useful in every case, but in some case where you're trying to calculate the power, at least one of these will be useful. The units of power are watts. The symbol is capital W, so this is confusing. You need to know whether you were talking about work done or watts. The context should be clear, okay? This W is in the equation. It's a variable. This W is a unit for watts, okay? You need to know the difference between them. Another way of saying a watt, if you look here, work is measured in joules over seconds, so you could have J over S for the units. And work is a scalar quantity. It is a quantity that you don't need to worry about the direction for, okay? Just the number is important. At this point, I don't have them in front of me, but I believe we have just gone through every single equation that is on the back of the reference tables. You can check me if you want, but this is good. We have gotten through the entire back of the reference tables at this point. You should know what every single one of those equations is, and you have used every single one of those equations at some point. So now, what it comes to in the last couple months of the year is we will go through the rest of the reference table. And trust me, it'll go much, much quicker than going through the back, which took us, approximately 6-ish months. Okay? Let's do some examples. A machine is rated to be able to do 2,400 joules of work in a minute. How much power does this machine develop in watts? So the key thing to remember here is it's asking in watts. Remember, watts is in joules per second. we know we're trying to find the power, and we're told how much work is done. So P equals W over T seems like a good equation. However, we are given the 2400 joules, but notice we're told the time frame of a minute. If we want the units to be in watts, which is joules per second, we can't just plug in 1 minute here because then the units would be joules per minute. That's not a watt. Instead, what we need to do is realize that a minute is 60 seconds. Plug that in instead and divide 2400 divided by 60, and we get 40 watts of power. So what we would say for this, this machine develops or generates 40 watts of power. That is the rate at which it can do work, the rate at which it can transfer energy. What it essentially says is 40 joules per second. It can transfer 40 joules of energy per second from one object to the next or from one type of energy into another type. Let's try another one. A power lifter can generate 625 watts as they lift a heavy weight 2 meters above their head over the course of an 8-second period of time. How much weight was lifted? Well, clearly this one's a little bit different, so let's label what we know. We know 625 watts, that's the power. The weight is going 2 meters above their head, so they're moving it 2 meters, so that's like a displacement, right? And this is over an 8-second period of time. Time is measured in T. We want to know how much weight is lifted, okay? When we talk about weight, we know that weight is a force. Specifically, it's the force of gravity. So what we're really looking for here, we have P, we have D, we have T. We're trying to find a force. Let's go up here. We know power, we know displacement, we know time. We're looking for this force. So we're going to use these two parts of the equation. P equals F times D over T. And specifically, this force is the force of gravity. So that's what I'm going to use from here on out. In this problem at least. 625 watts equals Fg times 2 meters divided by 8 seconds. In order to solve, I need to get Fg alone. I need to get rid of this 8 over here, so I'm going to multiply both sides by 8. 625 times 8 is 5,000. And then I'm going to divide both sides by 2 to get rid of that 2. So the force of gravity on this weight ends up being 2,500, and since it's a force, newtons. Now, that's not very helpful because we don't think in terms of newtons a lot. Let's try this. How much mass would that be? Okay, this is not the point of the problem. This is not what you're asked to solve for, but we might as well see if this makes sense. If we want to solve for the mass, we plug in the 2,500 newtons equals m times g is 9.81 meters per second squared. We divide the 2,500 by 9.81, and we end up with a mass of 254.84 kilograms, which comes out to a little bit more than 500 pounds. I believe, although I haven't kept up with my powerlifting competition recently, I haven't been paying attention, that seems like it's a little bit over 500 pounds, and that seems like it would be, a fair amount for a power lifter to, in fact, lift, okay? That would be a lot of mass. Let's do one more question, then we'll call it for this video, and we'll make another one. A crane lifts a metal beam with a mass of 1.5 times 10 to the 4th kilograms, a distance of 30 meters in 60 seconds. How much power does the crane generate? Very clearly, we're looking for P here. We know the mass of the beam the crane is lifting. We know the distance or displacement it's moving through, and we know the time. Okay, this one seems tricky. I have power, I have mass, displacement, and time. I don't see an equation with mass in it. Okay, well, I'm a little lost. Let's try this. Let's draw a free body diagram, see if that helps at all. Here is the beam that is being lifted up in the air. And the beam, let's see, let's call that an applied force. Let's call this a force of gravity. The net force on the beam, okay, this is looking familiar now. We have Fa minus Fg equals MAy. Again, let's assume a constant velocity just to make this very easy on ourselves. So Fa equals m times g. Now we might be able to get somewhere because I do know that the power is equal to force times displacement over time. And if we take that force to be the applied force used in lifting, then I think I can get somewhere. And that force in this case, is equal to the force of gravity, which is m times g times d over t. The mass is 1.5 times 10 to the fourth kilograms. G is 9.81 meters per second squared. D, 30 meters. T, 60 seconds. We plug all this in. 1.5 EE to the fourth times 9.81 times 30 divided by 60. We end up with 73,575 watts of power being generated by that crane. That crane can transfer a little over 73,000 joules of energy per second to that crane, to that beam, by lifting it up. I'll come back and do the last three in just a little bit.